Hey, good afternoon, everyone. I'm back. This is lecture number 5 in the GeoDBMS course. Um, Today, I do not have so many topics. I will start with this NoSQL presentation to teach you something else than SQL. And then I have 2 tiny topics, and um, in between I'll do a break. And I'm a bit, I was looking at presentations that I still have, and I'm almost done, I see. So um, I'm not sure I have much to talk about on next Friday. So I will check, and if you have anything you still want to know from databases or the SQL part, please let me know. Then I can make some extra lecture, and I'll check for myself whether there's anything I can tell. But if nothing pops up, then we have a break. We have extra time for doing your assignments on Friday. There's one question I heard that on Brightspace there is a possibility to fill in an evaluation for the lectures or the courses of the first quarter. Please fill it in if you can. And then I start now with this NoSQL thing. This is a project by a student of mine, Bart Baas. He did his graduation a few years ago. He came to me and said, "Well, I want to do this graduation thing, and I've heard about NoSQL databases. What can I do about it?" So at the time, together we constructed a master's thesis project, and this is the thesis that his final presentation I'm going to do now, and it gives you some insights in how to do tests with databases, and that there is more databases than only SQL databases, and it might be in a sort of inspiration for your own master project. So let's get started. So Bart, he this is his final presentation, and he started with the background, and this is basically what you do when you do a master's project. You start with the background, your objectives, your methodology, and then there's some slides on the details, what he really did, and then results, conclusions, etc. So where did he start? Well, at the time he was there were these databases, and everybody did databases were SQL, and now it turned out that a thing called NoSQL, and it's a bit weird because how can you define a thing being NoSQL by defining what it is not? And well, that's because SQL is this predominant standard in databases, and so everybody that's doing something else is basically doing NoSQL. And it turns out that it happens that so it's a broad class of databases. So each NoSQL database is different from another one that differ from classical relational databases in some significant way. And then, yeah, what ways it differs, and that's where the difference is between NoSQL databases, because some NoSQL databases do not use tables, and well, and some of them they do not use transactions or have different kinds of transactions, and that's why they can be faster, or they don't have transactions at all. So all of these NoSQL databases are different, but you have a sort of families of them. And here you have the family tree. So you have NoSQL databases, and one of kind of things that are always hard to store in relational databases are documents. And so there's many document storage systems where you still want to be able to query the documents in a way, and that is one special family family of NoSQL databases, and this one, MongoDB, is an interesting one. I think it stores documents or JSON objects. Another one is key value pair databases, another interesting family. Well, because one of the problems with people feel they have with SQL databases is that all the time if you create a database, you first have to make a data model, and you have to define exactly what columns there are. Can't we make a database where we just say, well, I have this object and I want to add this property to this object, and then it should fit. And this is called a key value database. Also, well, many applications, they're really useful. And then there's the graph database. Neo4j, the one that's discussed in this lecture, is one of them, so they will be discussed later. And then there's this final thing called column databases. And as you might have remembered from the first slide of my first lecture, I have been working on this database that was the fastest in the world, MonadDB, and that one is a column store. And in that database is kind of special because, well, normal databases, of normal SQL databases, you have always, you can have lots of columns in the database. And in this special column database, each table has only 2 columns. And that's what you, and you have to do it with that. And then the trick is that if you have a table with 10 columns, then you can split it in 10 tables with 2 columns, with lots of identifiers between the columns. And then if you have a really fast join mechanism, you can join all these 10 tables to make the big the big table again. And if you do that efficiently, it can be even faster than having one table with 10 columns. These are column stores. Okay, so there are lots of families, and graph databases will be discussed today. And well, basically for all the other databases, there's still options how they could be tested and compared with the SQL databases. So, well, the main objective of this student Bart's course was to analyze the advantages and disadvantages of the NoSQL data store Neo4j for spatial vector data as compared to the standard storage in PostJS. Because, well, that's what you get the next lecture, I think, or next week. You get storage in PostJS, and now you've been working with the PostgreSQL, and it's all kind of nice. And this is sort of de facto standard, and now he wants to try something else. Well, how did he start his research? Well, he started with subobjectives. He wanted to know the capabilities of current NoSQL databases. Well, basically because he started with this idea, I want to try a NoSQL database, but he didn't know which ones there were. So that was his first question. Then after some research, he figured out that Neo4j is a nice one to try. And then he tried and implemented some data sets and queries on these both systems, and then tried to compare them. And if you compare if you run the same query on both systems, you can use your stopwatch and see what the results are. And in this way, he tried to figure out which one, in which cases, this Neo4j would be an advantage above standard SQL. Because, oh yeah, standard SQL is used. It's basically the case that in 99% of the cases, a standard SQL database is okay. But if you have a special kind of data, then in some cases you need some NoSQL one. So this is his methodology. He started and he selected the NoSQL database. He did NoSQL literature research, and then he split up. Basically, he did a design of a system in NoSQL, and then designed the same system in Postgres. And then he compared the stuff, and then he came to conclusions. And then before starting to do the comparing of the two, he did some literature on how to compare databases. Because, well, the tricky thing is if you try this NoSQL database, in this case Neo4j, well, it's sort of it's a sort of rocket science. So it's really complicated to install, and well, it crashes, the documentation is not good, etc., etc. But for some specific cases, it's really fast. So it's not only objective measures like how fast it is, but it's also subjective measures like how much time it does take to program my solution and how stable it is, and do you think it will work after 20 years. So he devised an evaluation methodology, and then he also thought about benchmarking, because if you compare two databases on performance, usually that's called benchmarking. And well, it's always a big job if you do benchmarking of databases, because for example, many databases, especially commercial databases, if you buy it, in the small print of your contract says you cannot publish benchmarking results, and that's a bit tricky. So if you want to publish, if you want to do research on databases, and that's what you want at university, you have to be really careful, because the problem is, if you try a database out of the box and it doesn't perform, it doesn't mean that the database is bad, but it may also be the case that you implemented it the wrong way. So maybe you created the wrong index statements, etc. So always, if you are going to do serious benchmarking, you have to contact the vendor of the database, and then if you have the right context, then together with the vendor you can say, this is my plan, what I want to execute, and this is the results that they want to publish, and then they look over your shoulder while doing it, and then at the end you may publish the benchmarking results, but it's usually very tricky. Oh, I go back to this one. And then if you do benchmarking, so you test databases, it should be simple as possible, relevant, portable, and scalable. So, and that helps in other people performing the same test. So if you have a benchmark, then what you usually do is say, well, I use this data set, and it should be easy to get this data set, and it should be relevant or representative, this data set, and it should for others also be possible to acquire that data set, and it should be scalable. So, well, that's what you have with this Moore's law, that computers get twice as fast every 2 years. So if you want to redo the same test 2 years later, then it's nice if you have twice as much data, because otherwise it becomes too easy for a database system. So how did he do this, making a simple thing? That was the first requirement for his benchmark. Well, for both databases, he made a sort of user interface with a button saying I load, push, etc. So that was doable. And then that's kind of the first thing that he tests. Let's just connect to the database and see how much time it takes. And well, this is where he started. And well, so here you see he tested this on Neo4j and PostGIS, and well, yeah, you see a small time difference. It doesn't really matter, so this is okay. Let's continue. Then he thought it must be relevant. Well, then we have a GIS context. What is relevant in GIS context? Well, what we always do in GIS is we have a map, and we zoom into the specific rectangle on the map, and we want to see all the objects, or count them, or whatever, inside that rectangle. So that's what he tried. So basically, why would you count the objects and not just transfer them? Well, because counting is a database operation, and then if you transfer the objects because you want to have a look at them on the map, then you have to usually transfer them to a different computer, and that's basically a network thing. So for benchmarking, if you want to really benchmark a database and not the network, then you better count the objects instead of drawing them. So that's why you have count here. And then, of course, you want to get the data that's separate from this one, get the object, and then what you always want, what you sometimes want in databases or on a map is find the nearest object. And the idea was that because Neo4j is a graph database where near objects are linked, then Neo4j would be good at this one. And the final thing is with databases and graph databases, find shortest path. And so after some research, he decided to implement these 4 operations. And he did it in 2 systems. In PostGIS, he did it with SQL, of course. And here you have the SQL statement. These you can already read. Well, this part you cannot, but you will next week. This is just converting a polygon to a GML statement. And Neo4j, this other language, they had an other programming language. You have to, if you need to query a Neo4j database, you have to write a Java program. Java is a sort of Python, but then slightly different. And you create, it's called a pipeline, and then you iterate over the pipeline and you convert to GML. So the query languages are completely different, but here you have the same query for 2 systems. And then another requirement for a benchmark is that it should be portable. And well, he did that by using the OpenStreetMap dataset. I really hope that you know about this dataset. OpenStreetMap is a sort of Wikipedia for maps. And they have a really nice map. Just type openstreetmap.org in your browser and you see a really nice map. And the nice part of it, like with OpenStreetMap, is that you can download it completely. And if you download it, it's all in XML, and you can parse this. And there's, I don't see polygons or coordinates here, but they're also somewhere in the database or in the system or in the dataset. And everybody can download it, and that means portable, because before this benchmark, we once did the benchmark with all the parcels of the Dutch cadastre, and it was really nice, and we even managed to publish the data with or the benchmark results, and it was with Oracle, and Oracle, they agreed that we could publish the data, and then other people wanted to try the same benchmark or implement it, and then it turned out that these cadastral parcels, they were not open data at the time, so that didn't work. So if you make a benchmark, please use open portable data, and well, this OpenStreetMap is a nice data set for that. And then he wanted his requirement number 4 was that data benchmark should be scalable. And what he did, he started with, he defined 4 data sets. He started, I think he lived over here, the guy. So he had a really tiny data set for the village of Medemblik. Small data set, was a bit bigger. The city of Amsterdam, a bit bigger, the province of North Holland, and well, you also could try the Netherlands, but that didn't really work. And if you want to go really big, then you could have tried the whole world. So in a way, it was scalable. So if you implemented it on one scale, you could go to a bigger scale and see whether it worked there. So that was for benchmarking. Now we go to Neo4j. It's a graph database, and let's see what the graph database is. And then he stored the OpenStreetMap data into this graph database, and he shows also how to do that. What's a graph? Well, maybe you've got it in mathematics, but the graph usually is a collection of vertices and edges, and vertices are nodes, and edges are lines between nodes. And then you have Sometimes a directed graph, for example, is a graph where an edge from V1 to V3 is different from an edge from V3 to V1. And there's all different kinds of graphs. And you have spatial graphs there where the geometry of the edges is important. And but this is basically a graph. You have your database has nodes and edges. And Neo4j is a graph database. It had, and I go back to the previous slide. And in Neo4j, each node has properties like a type and other properties, and also edges have properties. And with these properties, you can make a whole structure, like you have OpenStreetMap, that's a graph, and it's spatial and layers. So this is a high-level picture of how we stored OpenStreetMap. And this is basically low level. And so there it turns out that in OpenStreetMap, you have nodes. That's where streets meet. And you can see here, if you can read the tiny coordinates, they have coordinates. And these nodes, they are connected and they have lineage. So sometimes nodes disappear and reappear. And what's more important, oh yes, in OpenStreetMap, a way, that's a sort of road, is a list of nodes. And so basically nodes are vertices of the spatial of your graph database, and ways are edges. And then to say that the road of a way, that it is a street, then you give it a specific tag, like the number of lanes, etc. And in this way, this whole OpenStreetMap becomes a graph database. You can map it to a graph database in Neo4j. And with that graph database, he did this queries. So, and he implemented the same thing in Postgres. So all this OpenStreetMap data was also loaded in Postgres. And then he started doing benchmarking. And now it becomes a bit more interesting, because here you can see that, well, to create a data set or to import it, well, for small data sets, it didn't take much time. And then you would expect, well, if you get a bigger data set, it will be similar. But then it turns out, if you start importing in Neo4j, if your data set becomes a bit too big, then basically the execution times explode. And well, this was 14,000 seconds, which is still doable, but I think he also tried on the whole data set of the Netherlands, and that worked on Neo4j, but he just, like here, he tried, he couldn't, it worked in PostJS, but he couldn't load the whole data set in Neo4j. And here you see one of these tricky things that we discussed before, because the bottleneck of databases usually is the disk. And so this Neo4j is a sort of memory-oriented database. So as long as your data set fits in the memory of your computer, and you do not have to go to disk, it's extremely fast. But if your data set is getting bigger than your memory, then it just doesn't work anymore. So what you conclude from this image already is that well, apparently the memory of this of Bart's computer was big enough to store Amsterdam, but it was not big enough to store the north of the Netherlands. But that gives a nice hint on the scalability of such a system. So you can predict in advance, if your data set is bigger than your memory, do not use. Well, that's a bit. Well, you shouldn't post a conclusion like this. But if a data set is bigger than your memory, then it's likely that Neo4j will get performance problems. Here, where he also looked at is how much disk do you need to store the data, because, well, as you know, storing data in a zip file is more efficient than storing data unzipped, and all these databases have different way of storing data internally. And well, you see for the small data sets it doesn't matter, but for north of Holland, you see that Neo4j needs twice as much disks as the other two systems. These were the basic raw files that were downloaded. And so, well, if you create a system, that's also a consideration. So that was the start of his research. Then he started doing queries like the bounding box count, finding all the objects within a given rectangle. Well, again, you see that Neo4j takes up more time than PostGIS, and getting the data of creating the GML. It's even, well, it's a bit worse, but similar, not much difference there. Well, this slide, yeah, I didn't know what Bart wanted to explain here, so I skipped this one. So then well, actually I remember from when he did his research, we became a bit worried because, well, we've been spending lots of time using this Neo4j, and basically everything that we tried on Neo4j, PostGIS, the default system, was much faster. So, we thought, is there anything where Neo4j might win? And well, then we thought, well, graph databases are good at graph algorithms and finding the shortest path with the graph algorithm. And yes, luckily, it turned out that if you wanted to do shortest path algorithms, then Neo4j was way faster than PostGIS. So that's good. So finally, we found the niche, and we were hoping in advance that there was one. So we found a niche where Neo4j is definitely faster. And well, if you want to have closest points, here again you see that well, the bigger the data set, that PostGIS is more scalable. So if you have a really big data set, it might not work that well on Neo4j. Memory footprint we also looked at. So Neo4j needs a lot of memory, and those were the objective results. So we also did some subjective results, because, well, why would you try new ways of using new databases? Well, this Neo4j is nice because you have a different language like Java instead of SQL, but SQL with C, and the Geo pipeline. So you have new query languages which might fit better the language that you're working anyway. And this Neo4j is schema-less, so you do not have to say which properties a database has in advance, and that's also convenient or modern. And well, you can embed it in any Java program, and it has built-in shortest path support. So this Neo4j has some nice extra functionalities which are okay, but then also PostGIS has subjective advantages, like it's mature, it never crashes, and it's properly documented, and that really helps. And well, the SQL with the S language is, well, it's nice, and even with short queries you can make interesting solve complicated questions, and it's flexible and all round, and everybody knows it. So both of them are, well, they have their own advantages, and then you have to come to conclusions. So, well, at least Neo4j is good in one thing: it's good at doing shortest path queries. By the way, PostGIS can do it too, but not so fast. Definitely PostGIS is more mature and versatile. And if you use Neo4j, well, make sure you plug in lots of memory in your computer. And well, the other thing you should really be careful about if you compare databases, well, this Neo4j is rocket science, and rockets, they crash once in a while, but then that's because more research and more development needs to be done. So um, if you have really a problem that no other um, tools can solve, like getting stuff into to the moon, then you need new technology. So one of the conclusions basically is if you have a problem that might only be solved by Neo4j, well, it really is an interesting option. And that comes to the main conclusion. So relational and non-relational, SQL and non-SQL, they will remain in use side by side, and each with a perfectly fit for their own capabilities. And his conclusion was there in June 2011. And 9 years later, we can definitely say this is the case, because in practice now, I use a sort of mix of SQL databases and NoSQL databases. Not Neo4j, by the way, but another one. Okay, so this was basically his research that I'm talking about, and this was he used for his presentation, or this is literature background, and this basically is well, research that if you start doing graduations in geomatics, you might try something similar as this. Okay, then now I have two topics left. I have a few slides on PHP and a few slides on table indexing. I suggest we have a 5-minute break. It's 14:70 now, and then at 14:22, I come back at you with for these final two. Okay, see you in 5 minutes. Okay, I'm back. I found one extra set of slides, so also I want to show some slides after the break about going from UML to SQL, so the first two parts that we did in this lecture. But first I start with this, why SQL is so important as a basis for the web, and what PHP is. Sometimes you see these websites where the URL ends at PHP, and it's a sort of programming language. And with this programming language, which is sort of mix of HTML and SQL, or then you can really make nice websites. And I just tried this once for myself. And so if you will build websites that want to be filled from databases, this PHP is the way to go. And there's even a word for it. It's called the LAMP architecture, and many computer systems or many data servers on the web, they work like this. It's LAMP, it's Linux, Apache, MySQL, and instead of MySQL, you can use PostgreSQL, and then on top you have PHP. So you have a computer system that runs Linux. On top of that, you have an Apache server as a web server. The M or P part is about where the data is coming from, and this is basically creating your programming logic. So now I show you this part, the PHP part. So with that, you can basically start building your own website. It's really a simple language again. Well, again, it depends a bit on what you like, but PHP is a sort of mix of HTML and SQL. So here, I wanted to create a website where I could have a look. You know, I'm always storing my own location history, and sometimes I wanted to create a website to browse my own location history. And then I started with the website. It's with HTML. And it starts with chapter 1. This is how websites look under the hood. And then here I wanted to make a table, and the table body with the table header. And inside this table, I wanted to, for each month, I wanted to show how many GPS points I had. So what you do then, in the same language, you connect to the database. You do some tricky stuff. I don't remember what it is doing. And here, then you start a query, find all the count all from the track points, and group them by month. This is oh yes, and this is the year that was coming. That was a parameter of the website. And then you execute the query, and you iterate again over the results. And well, this is looking tricky, but it's just printing the result in HTML style, and then you're done. So this tiny script results in a website that looks like this. It's HTML, and here you see nicely for each month of the year how many points in my GPS log I had. So basically you can see if I go on holiday, I carry the GPS a lot, and you get more points there. And so this is another language again that you should know about, that if you want to create websites, you could use PHP, and you can link it with your SQL knowledge. Okay, that was one set, PHP. Now I do one about table indexing. Not this one. This one. Because one of the questions of what is how do you create tables, or if you create a table, where do you put indexes? And well, it's pretty straightforward. So, for example, if you have this database with students, and well, the student ID, the student numbers, well, basically the identifier that you search on a lot if you do joins. So you make that, and you want it to be unique, so you make that primary key, and that automatically creates an index. So from that moment on, if you create a table like this with the primary key, searching on the student ID always is getting fast. And then, well, sometimes you also want to search on names. So then you could use this create index statement in Postgres, and it creates an index on students, on the table students, on the name of the students. And from that moment and on, also searching on the name will become fast. So, how does it work in the database? Well, basically, if you use a primary key in your create table statement, that basically means that the content of your data is sorted on disk, or is sorted on this primary key. So in this case, the student ID was the primary key, so your content was stored on the primary key, and that's really convenient, because then if you do it like that, then you know that students with IDs that are close to each other will also be close to each other, will be on the same disk block, which is convenient for database searches. And but then the problem is, you can only store you can only sort objects or a table on one table. It's like in an old-fashioned library, and maybe remember they still exist. Old-fashioned of a library still exists. So usually the books in the library, they are stored, or in the bookshop, they are stored on the name of the author or on topic. And then the problem comes if you want to search on another topic, like the title of the book. Well, you cannot walk through the library and find them, or you have a long walk to do. And a very long time ago, they had these index cards for this. So this drawer, they used to really be in libraries. You had index cards, and these index cards for each book in the library, there was an index card. And on the index card, you could find the name of the author, or the name of the title of the book, and then you could find the name of the author, and then you know, or there was a shelf mark, and then you knew if I want the book that is represented by this card, then you know where to walk through the library to go there. Well, basically that's exactly what's happening in databases if you create an index on a table. So the database itself is stored on the primary key, and an index is basically creating a bunch of papers like this, and it looks like this. Here you have your original table again, which is sorted on this identifier. And then if you type this create index statement, if you type this create index statement, an extra tiny table is created, and this table contains the name of is then sorted on the attribute that is mentioned in the index, and then it confers a reference to the primary key, so you know where to find the object in real life. So if you want to search, if this index is used and you search for a specific name, then you can search on the sorted table, and then you see, oh, delta 4. Oh, this is connected to 4384423, and I follow the arrow, and this is where the rest of the attributes is. So if you do this create indexing, or if you use this command, then this is basically created, and in this way it helps you finding the data faster. So that's index creating, and this is the final slide that I need to. This is completely different topic. It turns out that people, also me, and also the inventors of query languages, became a bit worried and tired of this create view thing when you do queries of databases. And well, what was the pattern? You see a lot that you do a create view. Here you create a view, then you do a query on the view, and then you have to drop the view again. And if you forget to drop it, then your database gets dirty with too many views, etc. So there was now in there is this new SQL statement. It's not from the SQL standard, but it works on basically all the databases. And it's similar to creating a view, but without having to create it. So you start with, and then the name of the view. And from that moment, you can use this view as if it this thing as if it is a view. So now you use that thing in your query, and here you have the semicolon. At the end of the semicolon, then your view or the with thing automatically gets dropped. So if you want to make queries that are better readable, then forget about the create view thing and do exactly the same, but then with the with statement. So that's slide set number 2. And then I have a final slide set on UML modeling again, and basically linking UML modeling and creating SQL statements. I have to start at the beginning. So you have UML and SQL. UML is a high-level modeling language that you know now, and SQL is this query language. How do you go from one to the other? Well, they already look really similar, but there are two things, especially relationships, need to be mapped in a special way. So let's see what we can do when going from UML to SQL. Okay, here we have a really simple UML diagram. You have a book, and the book has a title, ISBN, and number of pages. You have an author, and the author has a name and a social security number. That's all straightforward. And of course, for mapping tables or objects or classes is really straightforward. You definitely get the table with book and the column title, ISBN, and pages, and you get the table author with name and social security number. But how do you map this relationship to from UML to the database? Oh, here you have to create table part for this thing. You have to create a table part for this thing. And now, because each book has only one author, it could also be one star, but in this example, it's one. It fits nicely if you create a book table and you add one attribute. It's an integer, and it's not null because here it says every book has an author. So you cannot have book without an author, and it references the social security number of an author. So in this case, this is exactly this relationship is implemented by this attributes. So if you want to implement a relationship from UML to SQL, and one of the ends of the relationship has at most one, that's straightforward, because then you can add it as an attribute to the relationship. But then what happens in this case? Your model becomes closer to reality, and books can have more than one author, and authors can have more than one book. So then it's impossible to add an extra column to the book with the author, because there can be more than one. It doesn't fit. And the other way around, it's also not possible to add an extra attribute to the author saying which book he wrote, because there can be more than one. So if you have this in UML, what do you get for SQL? Well, basically what you do is you add an intermediate table. So you create the author table, you create the book table, and then in the middle, you create this relationship table, which basically says which author wrote which book. So it has a foreign key to book, and it has a foreign key to author. And then if an author wrote 2 books, this author identifier will be there twice in this table and 2 times with a different book. So this is basically how you go from UML diagrams to SQL statements. And as you can see, it's really straightforward. So why can't we do this automatically? And it can be done. And you need a real UML tool for it, so not one of the so the UML that you need a new UML tool where the diagram is not an image or a picture, but it's really the system understands the UML, what is behind it, and one of these tools is Enterprise Architect. And well, so these days people do not make their own create table statements anymore; they are done by UML. So first you create a UML diagram, and then you push the button and you automatically create table statement. I'm not going to do this live because I'm not sure this will work via the link. So I put I made some slides to show it. And if you want to try it for yourself and it doesn't work, please ask me, because sometimes the buttons in this really complicated UML tool are hard to find. But I'll show you on this tiny example. I use this example sometimes where we have a sort of text and we create a UML diagram for it. So in this UML diagram, we are make the tour de France it's about, and we wanted to make it a bit more interesting this year. So we decided to legalize drugs, partially. And so there are 3 categories of drugs. You have legal drugs and illegal drugs, and small drugs you can only small amounts. But then the Tour de France goes to France, and of course France is a decentralized country, and each department of France have different rules for the drugs. And I'm not sure it was this year the case, but sometimes even the tour ends or starts in a different country. And of course Germany is a very strict country, and there all the drugs are illegal. So this is the context, and now the idea is that you have to make a sort of database or a UML diagram that describes this tiny world, and then from that UML diagram we make a database that the organizer of the tour can use to find out what cocktail of drugs are best for a specific leg of the course. Like if it goes up, you need different ones, and if it's the amount of kilometers is small and it goes through a specific department. So this is basically what the assignment is. And then, well, I try to make a UML diagram out of it. And here you have the UML diagram. You have legs of the tour. Each leg, they should have an identifier. Each leg has a number of climbs, because that's important to know. It has a length in kilometers, and then a leg starts somewhere. So it starts in a department, and it finishes in a department, and it goes through some departments. So, and here you have modeling issues already, because I'm pretty sure that somewhere halfway the leg, the blood of the runners of the Tour de France is not going to be tested. So we don't want to know through which departments or the rules of the departments where the leg goes through. I guess it's only important where it starts and where it finished, and basically where it finishes. So here in this diagram you see already modeling issues, and those are typically the modeling issues that you had 2 weeks ago when you did the Warhammer thing. And then of each department, you want to know what drugs are legal in that department. That's a bit tricky to model because it's not a property of the drug, it's not a property of the department, but you have a sort of extra class saying is legal in, and that's related to a department and the drug. And if you know the combination of the department and the drug, then you can say, well, this is legal, illegal, or small amounts. So this UML diagram basically implements what you saw for text in the previous slide. Now, and then what I did, I draw this UML diagram in Enterprise Architect, and then I push a button, and actually I have to push the button twice because it's done in 2 steps, and then I have my create table statements. And why do I need to push the button twice? Well, because there's 2 steps going on. In the first step, you go from one type of UML diagram to another type of UML diagram. And in the second step, you create, from the second UML diagram, you create table statements. Let's see what happens. Well, this is just if you want to try it yourself, you have to push the configure button, find the settings, and then choose for the database types. You have to choose PostgreSQL over here, otherwise it doesn't work. And then behind here, you see I already created the UML diagram, and then in the design tab of the UML tool, you push the transform button, and then you choose as a language, you choose DDL, data definition language. That is the create table statement. And then what happens, it creates from your UML diagram, it creates a new UML diagram, and this UML diagram is closer to database tables, because, well, here you see, instead of having a class, you see that this is a table, this is a table, and here you have this PK thing, which is for primary key. So this is a sort of UML diagram on steroids. So it has lots of more information and all this extra information that you need for creating tables. So that was the first push of the button. I have this pimped UML diagram, and you see it has primary keys and foreign keys, etc. And then again, you have to find somewhere deep in the UML of in the software, and then you find export the DDL to a database schema, and then you push the button again, and then finally you get this. And here you see what you get. This is what you got. I got from pushing the button from the UML diagram, and here you see that somehow it automatically, I didn't create it, inserted this extra ID attribute, and I already had made it myself when I created the UML diagram. So this is too much to having 2 identifiers. So I need to do some post-processing to be able to use this create table statement, or I fix the UML. But well, the basic idea is that you well, do not have to create your own, make your own create table statements anymore. And for small projects like you did till now, it's not no problem. But for big projects, it's really convenient that you can be 100% sure that the create table statements that were implemented are exactly one-to-one to the UML model, because that's a nice part of this model-driven approach, or this approach where you push the buttons. You can be 100% sure that the UML model that you see, that is exactly what is implemented. Because, well, I see that in projects where they do it manually, then it always happens that there is a big difference between the UML and the create table statements, and nobody knows anymore which one of the 2 is true. So I'm a big advocate of doing this model-driven approach, and I showed you how to do it in this Enterprise Architect tool. Okay, that's it for today. We'll see each other on Wednesday, where we have SQL again. I'll let you know before Wednesday whether I still need the lecture time on Friday, or I'll let you know on Wednesday actually. And so we see each other in real life on Wednesday and maybe on Friday, and otherwise maybe at the exam. Okay, see you later. Bye-bye.
Bye.
Bye.